Okay, are there any questions before we begin? So next Monday I'm traveling to Washington for an NSF related stuff, so we need to reschedule that lecture that we will miss. So far I haven't had much travel this time. Normally I do travel a lot, but luckily we haven't done. But I have few coming up in April also, so we will try to reschedule it. Are you guys?
A video too, like if you already have a video, like
We could just record it and put
if
it.
you already have something, you just
It may not synchronize with what we are doing right now. I will. I mean, I have put all my previous version of this on YouTube. And there's a channel called CHELEC Kumar. Go there, you'll find. This time I've put more emphasis on model development than in the last time I gave this course. So it's 50-50 balance. Previously it was maybe 30-60 on the numerical part. So you'll find more numerical material in that lecture, I think. But I think we will try to make up the lecture. So the thing I was going to ask you was, would the spring break be venturing into your free time? But I don't think you'll have free time. You'll be busy with the project, I think. So otherwise we will try to do it on a couple of Fridays. Okay, if I miss Monday, maybe that Friday. Because Thursdays and Tuesdays I have the lab, so I'm kind of tied up with that undergraduate lab in the afternoon. So we are still continuing to explore the linear algebra related topics, which form the core of any numerical methods algorithm for solving algebraic equations, linear or nonlinear differential equations, etc. So we are building towards that. So today I want to continue with the eigenvalue problem, the algorithms, efficient algorithms. That's where the focus is. So of all the methods that we have seen so far, for direct methods, Gaussian elimination, value decomposition, Thomas algorithm, or some of the more efficient ones. Sparse algorithms are a class by themselves. And then we started seeing in the last class iterative methods, the Jacobi iteration, the Gauss-Seidel and successive relaxation method. And we introduced this idea of a fixed point iteration. And we're going to continue on the iterative methods to find the eigenvalues of a problem. And the reason that we need the eigenvalues is they are intimately related to stability analysis of any problem. So, and we don't want to know all the eigenvalues. We want to know those eigenvalues that are on the stability boundary. So what are the ideas that are available to selectively calculate a few eigenvalues in the certain neighborhood of a point that we are interested in. So we know what an eigenvalue problem is. Given a matrix A, if you multiply it by a vector x, if it returns the same vector x except for a scaling determined by lambda, we call that as the eigenvalue problem, and the vector x as the eigenvector and lambda as the eigenvalues. And the way to find those eigenvectors and eigenvalues is to solve this particular problem. So move this to the left hand side and write it as a minus lambda I multiplied by x equal to 0. We don't want x to be trivial. That means we have to make this as equal to 0, the determinant of that. And that provides us a condition, a polynomial in lambda, the same degree as the number of elements in A, row dimensions in A, linearly independent entries in A. So that gives us, if I have an n by n system, I have n eigenvalues. When you're discretizing partial differential equation, you might have 100,000 equations very easily, so 100,000 by 100,000, so there will be 100,000 eigenvalues. But I'm not interested in calculating, and it's one of the most difficult calculations in terms of the computational effort. So I'm interested only in calculating a few select ones. So that's what we are going to talk about today. Okay, so in principle, I can solve this problem to find all the eigenvalues and then the corresponding eigenvectors. Once I have the eigenvalue, I can put that in and solve for the eigenvectors. And for small dimensional systems, MATLAB has a routine called EIG that actually finds all the eigenvalues and gives them in a diagonal matrix, the eigenvalues along the diagonal, and an eigenvector in the form of a matrix with each row representing one eigenvector. Okay, so there is a corresponding polynomial, the so-called characteristic polynomial, which is of nth degree, the roots of which are the eigenvalues. And we have seen these ideas in your first assignment, where I asked you to kind of go through these calculations. But I'm not sure whether you have seen the concept of a left and the right eigenvector. If A is not symmetric, if I formulate an auxiliary problem which says y transpose times A is equal to y transpose times lambda. So y transpose is called the left eigenvector, whereas x that we had previously would be called the right eigenvector, because this eigenvector multiplies this matrix on the left, and it is a row vector. So we make it as a y prime. Y prime A equals y prime lambda. So you can do the same rearrangement and solve in exactly the same way. Okay? So you have, for a given matrix, if A is symmetric, whether you transpose it or not, you're going to get the same eigenvector. Right? If A is symmetric, there is no distinction between the left and the right eigenvector. Why is that? If I have A x transpose, what is that? That is x transpose A transpose. But if A transpose is the same as A, that means A is symmetric, then x transpose would correspond to y transpose. But if A is not symmetric, then this will give you a set of eigenvectors that will be called the left eigenvectors, okay, because they are operating from the left. The same problem, so the eigenvalues are the same. The eigenvalues are shared for both the left and the right eigenvector, but the vectors are different. The set of vectors y prime are different from the set of vectors x if A is not symmetric. And we say that these two sets of eigenvectors, the left eigenvector x and the right eigenvector y, and there are n of them, okay, are bi-orthogonal. What does that mean? It simply means if I take a vector from this set, y1, for example, and take a vector x2, they will be perpendicular to each other. A vector from the x set and a vector from the y set will be perpendicular to each other. Okay, and that's what bi-orthogonality means. And it's fairly easy to show. Okay, so what you do is you take the original problem Ax equal to lambda x and pre-multiplied by y prime. Okay, so this is Axi equals lambda I xi, and I'm pre-multiplying by yj. So this is for in terms of the index I. The next one I have Axi equals the next one I have is yja equals lambda j y. Okay? So that is the left eigenvector. First one, I'm associating Axi with lambda xi, and I'm pre-multiplying by yj. In the second one, I'm taking the left eigenvalue problem, which is lambda j and yj, and I'm post-multiplying it with xi. Okay, and my purpose is to show what I'm claiming here, that these two are bi-orthogonal. Okay, a set from x is perpendicular to the set from y. Why would I do that? By doing that, the left-hand side I have made the same. These are two different problems. Do you understand that? First one comes from the right eigenvectors. Second one comes from the left eigenvectors. But I have pre-multiplied the first one by yj and the post-multiplied the second one by xi. And then left-hand side is the same. I subtract one from the other. The left-hand side becomes 0. And here you have lambda I minus lambda j, lambda I minus lambda j, times yj transpose multiplied by xi. Okay? But I and j are two different vectors, right? So lambda I is different from lambda j. I have unique set of eigenvectors. So eigenvectors don't repeat in this particular case. Okay, and so this cannot be 0. So yj prime multiplied by xi must be equal to 0. What does that say? They are orthogonal, right? That is one vector from x space and one other vector from y space. They are perpendicular to each other for every I not equal to j. Okay, so that's a proof that these are biorthogonal. Now, why is this important? If A is not symmetric, you need a base. You need a basis to represent arbitrary vectors. Later on, we will use this idea to construct what is called the spectral representation of a solution. It's a very, very important idea. It will not be useful for solving algebraic systems. For solving algebraic systems, the best method is Gaussian elimination. Okay? But the spectral representation of a linear equation will give us ideas that are very effective for solving differential equations later on. The so-called collocation methods, spectral element methods, they are all derived from this concept. So it's an important concept. So to represent such solutions, we need a basis. And the eigenvectors provide us the natural basis for that. Why? Because they are linearly, if they are perpendicular to each other, what does it say? They are linearly independent, right? If you have linearly independent set of vectors, they form a basis to construct any other arbitrary vector as a linear combination of that basis. Okay, so that's the reason why this concept of orthogonality or extension of it as biorthogonality for non-symmetric matrices are important. Any questions on that? Have you seen these ideas before? Some of you have, some of you have not. So when we get into that situation, we will follow the slowest speed. Okay, so if you have questions, please do ask me so that we can clarify that. If you have never seen it, I think it's important for you to get a grasp for it. Now, so our goal, as I said, is to find those few select eigenvalues that are near some region, typically in the region of stability border. Okay, so one of the powerful methods is so-called power iteration. Iterative methods play a very important role in numerical methods. So the idea of a power iteration is the following, and it's very easy to understand why it works. So I give you a matrix A and ask you to calculate the largest eigenvalue. Okay, so how do you come up with a scheme that will give you the largest eigenvalue? One of the scheme that was kind of tried out, maybe by trial and error, is take any arbitrary vector, multiply it by A, and you get a next vector. Okay, so you take Z0, multiply it by A, you get Y1. You take Y1, scale it up, and call it Z1, and multiply it again, and you'll get Y2, and continue this series. So it's called an iterative series. Okay, this is called the power iteration, in fact. And what do you think will happen to that iteration scheme? Will it converge? If it converges, where will it converge? You say it won't converge. Why?
Then it keeps increasing.
Good point. If you keep multiplying it by A, the magnitude of that vector will keep on increasing. And that is why the second step is important. In the second step, what we do is we scale it back. Okay? So we take Z0, when P equal to 0, we take Z0 multiplied by A equal to Y1. And then Y1 is nothing but the scale version of Z1. Okay? So I take the largest element, for example, from Y1, divide everything by the largest element, and I would call this as K, K1. So K1 is scalar multiplied by Z1. So I would take Z1 and multiply it again to produce Y2. And I would scale Y2 again to produce Z3. Now do you think it will converge? Or is it
all the time?
Not all the time. Very good answer. Not all the time. But under certain conditions, when the largest eigenvalue is well isolated from other eigenvalues. If there are two eigenvalues that are very close to each other, or if the eigenvalue occurs with a multiplicity of 2, meaning that there are two eigenvalues with the same value 3 and 3, for example. Okay, then this method will get into difficulty, and we can understand what kind of difficulty we will get into if you are comfortable with this idea of a linear space. Okay, but what this does is, if the leading eigenvalue, the largest eigenvalue, is well separated from all the others, this method will converge to the eigenvector corresponding to the largest eigenvalue. Okay, and that's a statement. How do you know? Can you show that? Why does it work? Why does it give you the eigenvector corresponding to the largest eigenvalue? Because I just start with some arbitrary eigenvector, right? I mean, an arbitrary vector, initial vector. Do you understand what I posed? The problem was to find the largest eigenvalue of a given matrix A, not all of them. Okay, and the method, that algorithm that we came up with, is start with some arbitrary vector, keep multiplying it by A, scaling it after every time so that the vector doesn't grow in length. And the claim is that it will converge in the direction of the largest eigenvector. And then you can calculate the eigenvalue from that. And the reason that it works is the following. Z0 is your arbitrary eigenvector. Sorry, I keep saying eigenvector. Arbitrary initial vector, a guess vector. Right? So any guess vector can be represented as a linear combination of a set of basis vectors. Right? So if x1 to xn are the eigenvectors that are linearly independent, that form the basis, then I can write this as summation of alpha I xi. So here xi are the eigenvectors. Okay, so then what I'm doing is, we will not do this. The actual algorithm are the two lines that I showed you earlier. Multiplied by A, scale. Multiplied by A, scale. So you put a loop around that, and that will lead to the direction of the largest eigenvector. This is the explanation of why that works. Okay? So this is that 0 has a spectral representation. This is what we call a spectral representation because eigenvectors are called the spectrum of the matrix. Okay? And alpha A are some as of yet unknown constants. Okay? So it's a linear combination of all those n eigenvectors. So y1 is nothing but A times z0. This is the first step of my algorithm. Right? I take A multiplied by z0, I produce y1. But that is the same as the summation, like if I substitute for z0 from here to there, it is summation of alpha I A xi. Because here I just have alpha I xi, but that is multiplied by A. So every element will be multiplied by A xi. But what is A xi? It's simply lambda I xi. Okay? So that is a spectral representation of the new vector y1 that I have calculated. Okay? And y2 similarly is A times z1. But A times z1 is y1 over k1. I have scaled it. Right? So, and that would be the scaling factor, 1 over k1, multiplied by alpha I lambda I, this is this term, pre-multiplied by another A. Okay? And that once again I'm going to replace by lambda I xi. So you can see the second iteration raises the power of every eigenvalue to square. This is why it's called a power iteration. Okay? It's an iteration on powers of the eigenvalues. Do you have any questions on this? You see what is happening so far? Algebraically, right? And if you continue this, what you're going to get is the next time you will take a k2 out from the scaling of y2. So k1 times k2. And this will become lambda I to the power 3. And if you continue this p times, you will get 1 over, the pi stands for a product. Product of all the k values from k1, k2, kp. Okay? Multiplied by alpha I lambda I to the power p plus 1 xi. Okay, so this is a p plus 1 iteration from the p iteration. I'm not doing this, I'm just tracking the logic of how the calculations internally are represented. But all I'm doing in my calculation is only what I've shown here, and the scaling every time. Okay? Now, if I factor out lambda, see there are n values of eigenvalues, right? I pick the largest eigenvalue I can label them as y1, lambda 1, and I take that out. So I have lambda 1 to the power t plus 1. In order to compensate for that, I have to divide every lambda I by lambda 1 to the power t plus 1. But I know lambda 1 is my largest eigenvalue. So what does it tell you about this ratio? It will converge. It will go to 0 except for when I equal to 1. So this actually has n terms. But each one of those n terms, other than the first term, lambda 1, will be driven to 0 because this ratio will be less than 1. And it is raised to the power continuously, right? So what is happening is, initially I started with a vector that is somewhere in the space containing components in the x1 direction, x2 direction, x3 direction, etc., all the eigenvectors. But that is going to be aligning itself with x1 direction because all the other components are going to be driven to 0. There will be no x2, no x3, because they will all be multiplied by 0. But x1 will be multiplied by just alpha 1. Okay, this ratio will be 1. And that is the proof that my eventual vector y will be aligned in the same direction as x1. Do you follow what's the logic or not? No? Yes? Any questions on that? If you follow this logic, I'm going to ask you a question now to explain what would happen when lambda 1 is not a single largest eigenvalue. Okay? That is, imagine now you have a case, a matrix A that I give you, that has the eigenvalues occurring twice, the largest eigenvalue occurring twice. The largest eigenvalue is 5, but it occurs twice. 5, 5.
So I think we'll get 2 of them, so 10 as well. Right? So I think this would return eigenvalue, largest eigenvalue as 10. So adding.
Sorry, no, that's not true. I want you to really understand this concept of a space in which you take a vector and what does this do? This power essentially gets rid of the components of the higher eigenvectors, right? So eventually, if there were 2 eigenvalues with the same number, and these are the largest, all the other ones are less and they are driven to 0. Where would this vector be? It will be a linear combination of x1 and x2. There will be 2 eigenvectors corresponding to 3 and 3. There will be 2 eigenvalues, but there will be 2 eigenvectors corresponding to those. So this goes to a subspace of your n-dimensional space. It's a 2-dimensional space because eigenvalue occurs with a multiplicity of 2. Do you understand what I mean by multiplicity of 2, right? If an eigenvalue occurs with a multiplicity of 2, it means that there are 2 values. It occurs twice. The largest eigenvalue occurs twice. Okay? So there is a subspace in the eigenvector space where the 2 eigenvalues are the same. So the eigenvectors are, you can still construct 2 linearly independent eigenvectors there, but your vector is going to live in that space as a linear combination of those 2 eigenvectors. You cannot make it go to one or the other. Okay? So you cannot then uniquely pick your eigenvector corresponding to 3 and another one corresponding to 3. Okay, so you need to do other tricks. But this explains beautifully to me the idea of why the power iteration works, and when it fails, why it fails, under what conditions will it fail. It will fail if the eigenvalue that you are looking for occurs with a multiplicity of greater than 1. Okay, any questions on that? Okay. So what about the convergence rate? What can you say? How fast will the sequence converge? Meaning, how many iterations do I need to do before the eigenvector points in the same direction? That depends on the separation between that eigenvalue and the next eigenvalue. It depends on this ratio. If I have one at 3, another one at 2.999, they are very close to each other, right? So for the term 2.999 divided by 3 to be driven to 0, you need to do lots of iterations. But if the first eigenvalue is 3 and the second eigenvalue is 0.5, then the ratio would be 1/6 for the next one. And so that will be driven to 0 very quickly in few iterations. So the distance between the largest eigenvalue and the next largest eigenvalue determines how fast you will converge. We talked about multiplicity of 2. This is another interesting question. What would happen if the initial guess you make does not contain any component in the x1 direction? So I make an arbitrary decision. So if you really make an arbitrary decision, it will contain components in all directions. But I make a deliberate attempt to make a guess for z0 that has no component in the x1 direction, in the largest eigenvalue direction. Then what would happen? By phrasing the question, I have given you the answer. Right? It has no component in the x1 direction. What determines whether an arbitrary vector has a component each one of the directions? Alpha. So by saying that it doesn't have any component in the x1 direction, I'm saying alpha 1 is 0. Right? And if alpha 1 is 0 forever, that means it can never go to the x1 space. It will not give you the eigenvector corresponding to the largest eigenvalue. So it is these ideas, it gives you a way of thinking about constructing solutions, and when solutions fail, why it might fail. Okay, that's one of the important things that I have as an agenda for this course. But how do we develop these algorithms? Why do they work? And when they don't work, why don't they work? So here I have an algorithm implemented in MATLAB to illustrate how the power iteration works. Okay, so here you give the matrix T and the maximum number of iterations to try, and it gives you the vector V and something called the Rayleigh quotient, which is the value of the eigenvalue. Because what we are going to get in this sequence is y is equal to AZ, P and P plus 1. When you continue this sequence, you're going to get a vector. Where is the eigenvalue there? There isn't one, right? But you know that when you scale this eigenvector, it gives you the direction in the direction of the largest eigenvalue, right? So the magnitude of the vector really doesn't matter. It's just the direction that matters. So when you put that vector on A, it gives you the same vector. So once I have that, after I continue this sequence, what did I do? Okay, so after I continue the sequence, I get AZ equals some vector y, but both are pointing in the same direction, right? So what I have in the end is only the vector that is converged, right? So if I take that vector AY, it should be equal to lambda y after it has converged. Okay, so the question is, now I know this, I know A. How do I calculate lambda, the eigenvalue? That's what I'm interested in. The power iteration gives me the vector, the eigenvector, but I want to find the corresponding value of the eigenvalue. So how would I do that? The one way of doing that would be you pre-multiply this by y transpose both sides. Then, because you know y, that's a converged vector, right? So this is going to be a scalar and that's going to be a scalar. Okay, so y transpose AY divided by y transpose y is equal to your lambda. And this is called the Rayleigh quotient, which is an estimate of what the eigenvalue is. And that's what this program does. Okay? It gives you the vector V and it gives you the Rayleigh quotient, which is defined according to that. And that's a measure of the eigenvalue. So here you see T times Z nu transpose divided by Z nu transpose Z nu. Okay, after it is being scaled. So that tells us a powerful algorithm to find the largest eigenvalue. Okay, but I may be interested in an eigenvalue somewhere else. So how do I develop ideas to develop algorithms for other eigenvalues? Okay, and that's a very simple concept to implement algorithmically. So one of the things is so-called inverse iteration. Now the problem is find the smallest eigenvalue. Instead of saying find the largest eigenvalue, I tell you to find the smallest eigenvalue. So what do I do? The eigenvalue problem is still the same. Xi equals lambda xi. And xi is eigenvector, lambda eigenvalue. I'm interested only in the smallest one. So I pre-multiply by A inverse on both sides. Then I have A inverse A is equal to the identity matrix, and I take the lambda and take it to the other side. And that is equal to A inverse xi. Okay? What do you see immediately? How do I get the smallest eigenvalue?
Define some gamma as lambda and solve.
Exactly. So you define, I call it as mu I as 1 over lambda I. So this power iteration will always give you the largest eigenvalue. But power iteration on A will give you the largest eigenvalue. So what happens if I apply it on A inverse? Right? If I apply it on A inverse, it will give me the largest eigenvalue of A inverse. Right? Because this is still an eigenvalue problem on A inverse. And the power iteration always gives you the largest eigenvalue of that matrix. That's what you mean mu I. But mu I is nothing but 1 over lambda I. So that's going to be the smallest eigenvalue. So all I need to do to find the smallest eigenvalue using the power iteration is, instead of passing A, I pass A transpose, I mean A inverse. A inverse to that algorithm and do the iteration, power iteration. Start with arbitrary guess and go through that, and it will give me an eigenvector and the eigenvalue that will correspond to the smallest eigenvalue of the original problem. You solve the A inverse problem, the largest eigenvalue of the A inverse problem, that will give you the smallest eigenvalue of the original problem. Right? Any questions on that? And the logic is exactly the same. You need to expand it in spectral representation. Now, finding A inverse we saw is pretty challenging, but the best method for that is LU factorization. Okay? So, we want to do the power iteration in this form. Put some Z0 multiplied by A inverse, you get Y1, scale it, put it back. That is applying it on A inverse. But every time I don't want to invert and multiply. So what I'm doing is I'm going to take this to the left hand side and write it as Y A times YP plus 1 equals ZP. My initial guess is still Z0. But to find Y1, previously it was a simple matrix multiplication. Now what is it? Solution of a linear system. Because previously we just took Z multiplied by A to produce Y1. Now to find Y1, given Z0, my initial guess, I need to solve this linear system. But I'm not inverting it. Okay? And that's one way of doing it. You invert and you store the matrix, and then you just do matrix multiplication repeatedly. That will give you the largest eigenvalue of that problem, which turns out to be the smallest eigenvalue of the original problem. But what I'm telling you is, in the interest of efficiency, you recast this problem by taking it to the other side. Now you provide a guess that you solve for Y1. You need to solve a linear system of equations. What is the best way to solve the linear system of equation? LU factorization. Okay? So if you do the LU factorization once, then it's just a matter of putting different right-hand sides and getting the solution. And we saw that as the most efficient way. And that's why LU factorization is better than Gaussian elimination in some sense, because the factorization steps, the forward elimination, back substitution, are all done once and for all and stored in these LU factors. And inverting LU factorization, LU matrices is extremely simple. So the best way to solve this is take A, do an LU factorization, store these matrices, and then just matrix multiplication of the new method with U inverse and then the inverse. That's the most efficient way of implementing it. Do you understand that logic? Shift inverse iteration. And this is eventually going to lead into an algorithm that is coded in MATLAB, and a Fortran version of it is available freely called, what is it called? Arnoldi iteration scheme, which will find you a bunch of eigenvalues in some region in the space that you identify. But this tells you the key concept behind those Arnoldi resign schemes. So the idea is now shift inverse. So you want to find the eigenvalue, not the largest, not the smallest, but someone that is closest to a given eigenvalue. Suppose I have 100 eigenvalues. I have a 100 by 100 problem. The largest one is 100, the smallest one is 10. I want to find those eigenvalues that are near 30. Maybe 2 or 3 eigenvalues near 30. How do I do that? Right? So the algorithms that we have seen will tell me what 100 is, directly applied on A, will give me the 10 applied on the inverse of A, but I want to find eigenvalues close to 30. So this shift inverse operation helps you to do that. So sigma is called the shift operator. Okay? You specify 30 here. That means I want to find the eigenvalues close to the 30. How does that work? It works by the following logic. A minus sigma I inverse multiplied by xi equals mu xi. So I'm solving the eigenvalue problem for this matrix, A minus sigma I inverse. A is given, and I'm interested in finding the eigenvalues of A that lie closest to sigma. What does the transformation do?
It's just finding the eigenvalue, but instead of 0, it's using sigma as
So for this new matrix, A minus sigma I, the largest eigenvalue will be, the smallest eigenvalue will be close to sigma. Why smallest? Because it's the inverse matrix. Right? So this new matrix, the eigenvalues of this matrix will be, the smallest will be closest to sigma. Okay? So I just need to apply the power iteration on that idea. That means I'm actually going to find mu I, but once I know sigma, I can translate that into the original one. So that once you understand that concept, then the rest is just an explanation of why it works. But the way that you would apply it is you would construct this matrix, and because it involves inverse, you will recognize that moving to the right hand side, doing an LU decomposition on that would be the best way to do it. Okay? So that can be rewritten as 1 over mu I xi equals A minus sigma I xi. Just take this to the right hand side, take mu to the left hand side. So 1 over mu, that's the largest, or mu the smallest. Okay? And that can be split as A xi minus sigma I xi, but A xi is the same as lambda I xi. So the relationship between the eigenvalue that we are interested in, the eigenvalues that we are computing for this matrix, for this problem, which is mu I, and the shift factor is this. So if you tell the shift factor after calculating mu I, you can calculate lambda I. That will be closest to sigma. So this is the way that you would actually implement it. Right? So this would be the original problem, and you take it to the left-hand side, do an LU decomposition on this, and set up the power iteration method. The MATLAB code that I gave you can be easily changed to accommodate for all of these cases. Now, with these tools, you have a powerful way of calculating eigenvalue anywhere in the problem, okay, that is closest to a given value. Any questions on that?
So, like you said, we can find 2 or 3 eigenvalues close to 30, but when you talk about power method, you said you can only find one term.
Power method will give you only one. The power method gives you always the largest eigenvalue, but we trick it by changing the inverse or the shift inverse operator to find anywhere else, but only one
So
eigenvalue.
if we keep 30 here as sigma, then we'll just get one eigenvalue close to 30, right? Or we'll
Yeah.
get more.
You'll get only one, closest to 30. Right, right. But if you want to find the next one, what do you do?
Just pick some other, like 30.
Right, so you will get closest to that one, right? So what you can do is, once you have found the one closest to that, shift it to that. Subtract sigma by that value. And then you will find the next closest to that one. So this idea is called deflation technique.
So if we pick sigma as eigenvalue, then it's not going to show the same eigenvalue. It's going to show something. Like if 30 is itself is eigenvalue, and if we pick 30 as sigma, then it's not going to show 30, but it's going to show the other one.
No. It will go. If that is an eigenvalue, it will go to that one.
Yeah.
Right. Yeah. Because that you understand from the expansion, right? Because that ratio will become 1, and that will be the vector to which it will align itself eventually. Right. Yeah. So you need to shift it away from that, close to But the more general expansion of this idea is this so-called Arnoldi method. That is what is implemented in MATLAB EIGS. EIG gives you all the eigenvalues, but it's good only for small systems. If you give a 100,000 matrix, it will take forever to calculate all the eigenvalues, right? But if you want to take a subset of eigenvalues, 10 eigenvalues close to some sigma value, then EIGS does that. So you did that in your first assignment. What it does is it constructs 10 vectors. Okay, from successive iteration, it will keep the 10 vectors. So you put Z0, get Y1. In the current method, you rescale Y1 and apply it and get Y2 and repeat it, but you take only one. In that method, you will collect the first 10 eigenvectors, and then you act on them as a bunch of 10 eigenvectors. And what it does is it spans a space of 10 eigenvalues. Okay, and this is the idea that is also used in another method that we are going to see in the conjugate gradient method. Okay, and these are a class of methods. What are they called? Generalized minimum residual methods or something like that. Yeah, so the idea is you learn to operate not just on one vector at a time, but a group of vectors to converge on a subspace, and then find the problem in that subspace. So I have a few examples here on how to do this. So EAG and the inverse power iteration scheme, and then there is one I think on the shift inverse. So you may want to just study this examples. Now we saw the spectral representation of any arbitrary vector as a way to understand why the power iteration works, to give you a particular eigenvalue that we want. Now we can also use the same idea to construct solutions to a set of equations Ax equal to b. Okay, that means I need to construct a vector x when I multiply that by a gives me b. So I'm given a and b, I need to find x. Again, Gaussian elimination is the best way to do it, but there is a spectral representation of the solution, and that is extremely helpful in understanding how this method works and then extending it to solving particularly differential equations, collocation methods, etc. So finite element methods, for example, is also based on that idea. So what is the idea here? So if you give me A, I know that it has a set of eigenvectors that are linearly independent, so that can form a basis. So I'm going to call these eigenvectors as EI, E1, E2, all the way to En. You are also giving me a vector B, which is the forcing function. You gave me a matrix, from that I constructed E1 to En, and then you also gave me a B. B is some arbitrary vector. I can represent that as a linear combination of the eigenvectors. So this is, E is the basis vector. Okay? So do you understand the idea of what a basis vector is, right? It represents a basis for you to, as a linear combination, represent any other vector. So in this representation, beta is unknown. I need to find what are the betas in such a way that I can represent this vector. How would I do that? I give you the basis vectors and I tell them that E1 is perpendicular to E2, etc. They are orthonormal, right? So I give you those set of vectors and I give you this vector B and I say find beta j. How would you do that? There is embedded an important idea later on that we will come across called orthogonality of functions, for example. Okay, that's important in constructing solutions to arbitrary solutions to differential equations, which are represented as arbitrary functions, as a linear combination of orthogonal functions. If you have done the math course in chemical engineering, some of you, right? You've seen this Sturm level theory. What do you learn in that? All the Bessel functions are orthogonal to each other, right? J0 is perpendicular to J1. Now you might scratch your head and say, what does it mean to say a function is perpendicular to the other? A vector perpendicular to the other we can geometrically visualize, and we can also see that E1 dot E2 is equal to 0. The inner product between those two vectors is 0. But if I give you two functions and say they are orthogonal, you define an inner product between those two functions as an integral, and that integral is 0, right? And that's an important concept. So if you use this representation, my question to you now is, how will I get all these betas? And you have done that. Those that have done the course, you have done that in representing solutions in terms of Bessel series or Legendre series or whatever polynomials are. All you need to do is take B and multiply it by EI. EI dot B on the left hand side. And on the right hand side, you do the same thing. Bj EI dot EJ. Okay? So on both sides, I'm multiplying, pre-multiplying by EI. This is the dot product. I know EI, I know B. So this is going to be a number, a scalar number. Right? Similarly, in the summation, beta j multiplied by EI EJ. That's a series. But what happens to that series?
It's 0 except when I equals to
It is 0 except when I is equal to j, because these functions are all perpendicular to each other. They are orthogonal, right? So this allows you to select one component at a time. So this immediately gives you the vector beta I. Beta I is nothing but EI dot B. So if you give me A, first I find all the E vectors, then you give me B, I construct all these beta coefficients. Okay, because I know B, I know all the E's. Right? So and if I take that beta coefficient, plug it, multiplied by the basis vectors, I will get B. So that's a spectral representation of an arbitrary vector, known vector B, in terms of the coefficients. But what I really want to do is construct the solution X in terms of alpha I, E, I. This I don't know, right? This I know. So this I don't know. Do you understand? So my goal is to get a spectral representation of solution to this problem. That means represent this in the form of its spectrum, eigenvectors. Okay. So how would I do that? So this is what I want to do. The way I do that is I go back to my original equation Ax equal to B. On the right hand side, I substitute its spectral representation. I just constructed. I calculated all the beta. I know that, right? So I can take B and represent it in its spectral representation. On the left hand side, I take this and substitute for Ax in terms of A times alpha j Ej. But I don't know every one of those alpha j's yet. Okay? But what do I know? I do know that A times Ej is lambda j times Ej. That is the definition for the eigenvalue problem. Okay, so now I can combine both the terms, the left hand side and right hand side term, and write it as lambda j alpha j ej minus beta j ej equal to 0. That is lambda j alpha j minus beta j times ej is equal to 0. Just algebraic manipulation. From this point, you need to use your head. Okay. So if this condition is true, what can you say about the coefficients lambda j alpha j minus beta j? What do you know? You know that ej's are linearly independent. So that means all the coefficients multiplying ej's must be 0. The only way you can satisfy this equation, these are not 0. They are independent of each other. Right? So the only way that you can satisfy this is each one of them is equal to 0. These kind of conditions you would use in the Sturm level problem when you're finding boundary conditions and initial conditions. Right? So the same idea. So that gives you lambda j alpha j minus beta j equal to 0, or alpha j is equal to beta j over lambda j. You know beta j, you know lambda j, the eigenvalues. So you have now found out what alpha j is. Once you know alpha j, you know the solution, because you already know what the eigenvectors are. So now you have calculated what alpha j is. You plug that in and you know the solution. That's your spectral representation of the solution to the problem Ax equal to b. Is it an efficient method? It's an elegant method because it gives us ideas on how to construct solutions to differential equations, etc. later on. But as an algorithm, it is implementable. What do you need to do to implement it? If you give me A, I need to go and solve the eigenvalue problem. I need to find all the eigenvalues and all the eigenvectors. Then I need to find beta. Then I need to find alpha from this. And then I have the solution. So the solving the eigenvalue problem for all eigenvalues is a very demanding problem computationally. So you never solve Ax equal to b this way. You always use Gaussian elimination or LU decomposition. Okay? But the idea behind representing this is very useful in understanding how we generalize this to the differential equations later on. Any questions on that? No? So the next important idea is this idea of minimization of residuals, because the method of weighted residuals and all the algorithms that are based in COMSOL actually comes from finite element method, which is based on this idea of a weak variational formulation and minimizing, finding the function that minimizes some sort of a residual. So the idea is very easy to grasp for an algebraic equation, and then you'll be able to extend it. So the problem is Ax equal to b. But now A is not a square matrix. That means you don't have a well-posed problem. Okay? You have m by n, m greater than n. What does this say? There are more equations than unknowns. What do you do? Is there a solution to that problem? It's really not, you cannot find a unique solution unless you reformulate it in a particular way that adds additional constraints on that. Okay, because there may be no solution at all that satisfies, because there are too many equations, too few unknowns. So you can take a subset of n by n, solve it, and then you try to put it into the rest and see whether it satisfies it. It won't. You live with the error, right? And so one general way of doing that is to define a residual as Ax minus b. The residual is a vector function. Okay? Because Ax minus b is a vector function. A is a matrix, n by n, multiplied by n by 1 will give you n by 1. And b is n by 1. Okay? So this is going to be n by 1, the residual of. We know that we cannot make the residual equal to 0 in this case. Okay? And so what we do is we construct an objective function phi of x, which is the norm of R. Okay, so that one way of defining the norm is essentially take the inner product between the residual vectors. Okay? So the residual vector is a measure of the length of the error between the left hand side and right hand side. Ax minus b is the difference between the left hand side and right hand side. It's a vector, it has a certain length. And we want to make that length as small as possible. Okay? So we define the length as this metric, this measure, and we try to search the space of x in such a way that vector length is reduced, minimized. So this is why it's called the minimization of the residual, method of weighted residuals. You can define this inner product in a number of ways. If you add additional weighting functions, then you will make this correspond to the weighted residual. Here there is no weighting. But this is going to be a scalar function. Okay? So it will be m by 1 for r, and you'll have 1 by n multiplied by n, 1 by m multiplied by n by 1. So it will be 1 by 1. So you can treat that as a function of a vector x. This is a scalar function of a vector x. And it's going to have some sort of a curve like that. Why do you say it's going to have a curve like that? It's quadratic in x. It's like a parabola. Right? So as I change x, the function phi, which is the residual, is going to map into something like this. And what I want to find is this, that value of x that makes that function the smallest. So phi of x plus delta should be greater than phi of x. If I find some value here and I perturb it by delta, no matter how I perturb it, it's an n-dimensional problem. Remember, this is going to be a parabola in a hyperspace, right? Because x is a vector. X is a vector, right? It's a scalar function, but a scalar function in a vector space. So I can perturb x in one direction, I can perturb x in the other direction, in the third direction, etc. Whichever direction I perturb it, it should always give me a greater value than the present one. And that says that I have achieved the minimum. Am I going fast? Are you guys, have you seen this? If you have seen this, we can move fast. But if you have not, you should perhaps slow down. But you need to ask me to slow down. Any questions? Are you conceptually following? You may have to listen to it one more time or read over it, but you're following the basic idea, right? The next algebraic steps are not very difficult, but kind of tedious. Number of steps are involved in here. Okay, but this is my basic principle. This is the principle of minimization of the residual. Okay. So the function phi itself is ax minus b transpose multiplied by ax minus b. This is my function phi, which is a function of x, which is a vector. But phi is a scalar function. So I do an expansion of this, term by term expansion. So that is, if you can follow what is written next, so the product of the first term with this one. Remember, I have a transpose operating on that. So it will be the transpose operating on ax will give you x transpose a transpose, and then multiplied by ax. Okay. Then I take this term multiplied with b. That's going to be x transpose a transpose multiplied by b. Then I take this term multiplied with ax. So that is b transpose multiplied by ax, and b transpose with b. Okay. So that's essentially expansion, expanding the product across those two terms. Okay, so here you notice that transpose of this term is the same as this term. Once again, you need to apply the transpose on the products. If you have transpose of b transpose ax, what would that be? You can write it, for example, as ax transpose B. And then you apply this on this one. So it's X transpose A transpose B. Right? Which is the same as the other term that I have, X transpose A transpose B. So I've combined these two terms to write it as 2 times X transpose A R transpose B. So I've just combined these two terms, and so the 4 terms become the 3 terms. So this is the expansion for my objective function phi of X. The next step gets even more difficult. Okay? Algebraically, conceptually it's not difficult. Now what do I want to do? I want to perturb this X by a small amount. The delta vector is an arbitrary vector. Okay? So I'm multiplying, I'm adding some arbitrary vector to X, I'm subtracting from the original vector. What do I want this difference to be? To satisfy this, I want this difference to be always greater than 0. Okay? For any arbitrary delta, I want this difference to be greater than 0. If that is true, then I have found a true minimum. Yeah.
So I couldn't get that, like B transpose AX, isn't the transpose of that supposed to be X transpose A transpose B?
This one?
Yeah, so the transpose of that is X transpose A transpose B, right?
Yeah, that's what I wrote, but I did it in 2 steps. So
No,
what I did was
that is fine, but like you said, you replaced that to have 2x in the equations typed.
yeah.
So you just move B transpose AX to B X transpose A transpose B.
So you have X transpose A transpose B, and I have B transpose AX.
What is the transpose of the previous one?
Why did I transpose this? You mean?
Yeah, it's not a transpose of that. Right?
That's a good point. Actually. Yeah. Thank you for catching me on that. But remember, this is just a scalar number. So whether I do it in, if it's a scalar number, what's the transpose of a scalar number? It's the same, right? So I can take the transpose of this, and I'm going to get the same number. But I'm just showing symbolically that it is the same as this, so I can write it as twice that. Okay, but yeah, that's a good point. So the reason I was arbitrarily taking the transpose of this is because it's a scalar number, right? So every term in this one is a scalar number. Good point. Okay. So the next one is again similar expansion, but my goal is to show that what are the conditions required to make this number phi of x plus delta minus phi of x to be greater than 0. Okay? If I found that condition, then that means for any arbitrary delta, I am at the minimum, because whichever direction I take in delta, my value will only increase. I have found the true minimum of that quadratic expression. And because it is a quadratic expression, there is only one true minimum. Okay? This is very similar to what you do for finding the minimum in calculus. What do you do in calculus? You simply take the derivative and set the derivative equal to 0, right? So this is the same idea, but you are going to now learn to apply to not only vectors like this, you're going to learn to apply to functions. And that is the calculus of variations. The whole area of calculus of variations is how to find functions that minimize certain objective function. Okay, function of functions. These are called functionals. And we will see later on in the method of weighted residuals and other methods on COMSOL are based on that idea of a weak variational formulation and minimization of integrals. Okay, so now let's get ready for the next algebraic manipulation. So phi of x plus delta, what it means is wherever I had x, I need to put x plus delta. So x plus delta transpose A transpose A x plus delta minus 2 of x plus delta A B plus B transpose A. That's the entire first term. Minus phi of x. Phi of x is x transpose A transpose A x minus 2 of, that's exactly the same. So I'm taking the difference between two functions, x plus delta, which is given by this, where wherever I had x, I replaced it by x plus delta, minus phi of x, which is the second term. And then I carry out expansion one more time. Okay? That is x transpose A transpose A x, x transpose A transpose A delta, etc. And when you do that, you're going to get the terms, the next two lines. I have identified by color code terms that are exactly the same. And what you'll find is that the yellow terms cancel out, the cyan terms cancel out, and the green terms cancel out too. They are exactly the same with the minus sign. And what you are left with can be written as A delta, that is the red term. Okay? So this is nothing but the inner product of A delta. Okay? That's a square. So that has to be a positive definite term, because the same vector A delta, transpose of A delta multiplied by that. Okay? Since delta is arbitrary and not zero, square of that must be a positive number. Okay? And then whatever you are left with is 2 delta multiplied by A transpose A x minus A transpose B. 2 delta comes over as a factor. That must be greater than 0. Okay? Pardon me? You have never seen this notation? I've used it twice already here. My apologies, you should have asked me earlier. I think I used it somewhere else. It's essentially so-called L2 norm or a square norm. That is, if you're given a vector, how do you find the length of the vector? Basically, they find the inner product. So in this case, that essentially what it means is, if you take A delta transpose multiplied by A delta. Okay, so A delta is a vector. A is a matrix, delta is an arbitrary vector. So A delta will give you a vector. Take the transpose of it multiplied by itself, it will give you the norm. This symbol essentially says that it is a square norm. The norm is what? It's a measure of the length of the vector. So there are many, many definitions for the norm.
I think the second norm is the square root of the square of every element in the vector.
Right, this is just a square of that. So this is the 2 above simply tells you that it's a square of the quadratic norm. That's just a nomenclature that is used for representing a norm. If you put 2 bars between a vector, it says it's a measure of the length. But you can have a maximum norm which says I'm going to take the maximum element of the vector and use that to represent its length. Or you can actually do square root of sum of all the square terms, which is the traditional Pythagorean definition of a length of a vector, right?
What is the term in the brackets greater than 0?
You mean this one?
A transpose AX minus A transpose B.
No, I'm not saying this is 0. All I'm saying is I want phi of x plus delta to be greater than phi of x. That means the difference must be greater than 0. Phi of x plus delta minus phi of x must be greater than 0 for phi of x plus delta to be greater than phi of x. Why is that? Because I want x to be my minimum. From that minimum, if I take arbitrary delta in any direction, I want the number to be bigger than that. And now what I've done is I've calculated what the difference is, phi of x plus delta minus phi of x. That difference is this. And that must be greater than 0 to have a true minimum. Okay. Now I'm going to ask the question, what condition should be satisfied on these terms to satisfy this greater than 0? I know that this is always greater than 0, right? But this can be less than 0, right? Because delta is entirely arbitrary, right? I can take a negative 1, for example, if I want, right? So the only way I can guarantee that this will be greater than 0 is if I make this deliberately 0. Right? If I make this term exactly equal to 0, then it will always be greater than 0. And this can be any arbitrary value. Right? This can be any arbitrary value, but this term must be 0. That is the condition for minimum. Okay? So from what I've done is I've derived a condition for minimum that simply says that A transpose AX is equal to A transpose B. If this condition is satisfied, I know I have found the value of x that minimizes the residuals. Minimizes the residuals of what? Ax minus b equal to r. Okay?
Isn't that just AX equals to B?
Hmm?
Is it the left one? Is it just AX equals to B?
It's not. Because this is the beauty of this. Ax equal to b was not even a well-posed problem. This was m by n. This is n by 1. So I had an m by 1 equations. But A transpose A makes it a square matrix.
Yeah.
If this is m by n, this is n by m. Okay? So this makes it a beautiful square matrix that you can solve. And you will know then that you are getting the solution that is minimizes this residual. Okay? So you have transformed the problem into a problem that is well posed, but that at the same time minimizes the residual. Right? It's a very elegant method to look at minimization concept for the first time for an ill-posed problem that has a residual that is not 0. And you know that you can make it into 0. Okay, any questions? So this is the so-called normal equation. If you're given Ax equal to b that is not square matrix, you formulate this augmented matrix and solve this square matrix, and you will get a solution that minimizes the original problem. Now, I'm going to just talk about conceptually what conjugate gradient method is, because there are a lot of powerful ideas there too, and we should take that in slow steps so that we appreciate the full ideas. But what is conjugate gradient method? It is a method to find the minimum of not just a quadratic function for more complicated function. It is also used for solving Ax equal to b. The CGS routine that you have used in your first assignment, conjugate gradient scheme, in MATLAB, implements this particular algorithm. And the algorithm is kind of closely related to what we are seeing, but what we have seen, we have formulated in such a way that you can use any method, direct method, LU decomposition. You just have to apply it on this matrix, A transpose A. You can use Gaussian elimination, whatever it is, because this is now a well-posed problem. Okay? But if you want to solve it iteratively, like in the fixed point iteration, conjugate gradient is one of the most powerful and simple methods. Just 10-line code, and it does a wonderful job of finding the solution in the least number of iterations. What does it do? So this is a sketch of that function phi you can think of, okay, that we just talked about as a function of x. This is an illustration in a two-dimensional space where you have x1 and x2. But you have to imagine that you have a higher dimensional space. And these lines in blue that you see are contour lines. What are contour lines? These are lines that have the same value of phi on that curve. Wherever you go, as long as you are on the same curve, it has the same value of phi. But as you go from one curve to the other curve, the phi value changes. Okay? So our problem is to solve Ax equal to b by a trial and error method. We have seen the Jacobi iteration, the successive over relaxation, etc. But the conjugate gradient method takes a different approach. It says, give me a vector x0, my initial guess. It's a vector, a complete vector for x. Then what I will do is I will calculate the gradient of that for the residual function. Because if I know the function, I can take the derivative of that and find the gradient. So the gradient vector gives me the direction. The direction in which the function changes the most. Okay? So if I'm on the same curve, the function is not changing at all because it's a contour. So to go from this to the maximum gradient, I should find the shortest distance, because that's the maximum variation in the smallest distance. Right? So the steepest descent, or the descent, the gradient method, finds a direction given x0, using the information about the gradient, find the direction in which I should take. So the vector guess for the direction is made. Next thing I need to know is how far should I go along the direction? Should I just go and stop here? Should I go and stop there? And there is an optimization problem there. So it finds the optimal length. And then at that point, it calculates the gradient again. The gradient is like this. It will take the next step in that direction. So you need to calculate a series of vectors, okay, as successive guesses, and the guess should take you to the minimum of this function, which is the solution to that problem. Okay, so that is essentially conceptually the idea behind what a conjugate gradient method is. Any questions on that?
So if we change the gradient in every contour, then it's going to take more memory. That's why they will do it at every contour.
You don't actually calculate the gradient, and that's a clever way of kind of estimating what the direction vector should be, and that algorithm is what we are going to talk about in the next class. Okay, so we are using the idea of orthogonality here to say, okay, I've taken some initial direction, and the next direction I'm going to take is kind of perpendicular to that, because I've exhausted the variability in that direction. And then every time I take perpendicular directions like that. And to determine how far I go, I use this the gradient function to see how fast it changes. And once again, we will use concepts of spectral representation, etc., to construct that algorithm. But the algorithm itself is just a few lines. The same idea that you see. Define the residual, and this is the algorithm. Okay? But you need to understand the logic behind every one of these steps, and that includes ideas from power iteration, it includes ideas from spectral representation, etc. So it's one of the most advanced algorithms in that sense. The ideas involved are fairly sophisticated. So we'll stop there and then pick up in the next class. I wanted to finish it by now, but I think this is an important idea. So.